Okay, so lesson 4, welcome. I'm going to kind of zoom through both this and 6.5 at the same time because you should have already kind of seen everything these lessons include in doing those two kind of explorations. So just to draw your attention to some key terminology, we call these trig functions periodic functions because they repeat themselves over a specific interval. Okay, so it repeats its values over an interval. The period of the function is the cycle along the horizontal axis in which it repeats. Okay, so how long the interval or cycle takes to repeat along the x-axis. Okay. Sine and cosine functions are known as sinusoidal functions. So if you hear that language, we're talking about the sine and cosine functions. Note that this is not specifically referring to tan. Because tan is actually not continuous in the same way. So it's a little bit different. The first word that we should really be aware of when we're describing these graphs is the amplitude, because it's kind of set in stone for a standard sine or cosine graph, aka the parent functions. And this is considered the maximum or minimum point from the midpoint line, or you'll hear me call it the midline. So if we are to graph sine x on the interval from negative 2 pi to pi, my maximum y value, or sine, remembering that sine actually, when we look at our unit circle, is the y coordinate. And again, you would have done this in your first activity. Okay. So we look, and our maximum value on the unit circle is positive 1, and our minimum value is negative 1. So our graph is never actually going to exceed or go below 1 or negative 1. So I can automatically set those values here on my y-axis. And always label your axes. It's a good practice. You can lose marks on the provincial. From here, I'm also going to set my domain. I know that I am going all the way to negative 2 pi. And so I'll just set up those values now. Okay, and you can subdivide it. Oops, not for as much as you want or as little as you want, especially once you become more and more familiar with these graphs. You'll have to use fewer points. So 5 pi over 4, 7 pi over 4, and again, all of these are negatives. Okay, and on the reverse side, we're going at approximately the same distance. And I may or may not label everything. I might put more ticks and just label some key points. Okay, my zeros are going to be at 0 radians. So I know that my point, I'm going to have a point here. When I get to pi radians, I'm also going to be at 0. And when I get to 2 pi. Conversely, if I go backwards, I'm going to end up with the same thing, negative pi, negative 2 pi. Okay, so all of those ones are pre-established. That's the only time I'm hitting 0. I'm going to get my maximums at pi over 2. And I hit my minimum at 3 pi over 2. Working backwards, I hit my minimum first at negative pi over 2. I've only gone backwards by 90 degrees, if you want to think about it in terms of degrees. And again, these are roughly drawn. And I hit my maximum at negative 3 pi over 2, because that's coterminal with pi over 2. Now that I have these points, I can go into my exact values like you did in the example, but I've been drawing these kind of graphs for a while, so I'm going to skip over those points because you should have done them. And what your graph is going to look like is something along. That's a little too much. So you really want to be very conscious that your curve at the top and your curve at the bottom are not V's. And so that's probably the trickiest part. Sometimes I like to kind of make sure they're not V'd by starting at those curves. And then you can kind of try and smooth it out. So again, my graph is not perfect. Especially since I've drawn the scale in here, okay? Same thing happens on this side. And I like to start at those maximum and minimum so I get to ensure they don't look like V's per se. This side looks much better than this side does. And that fulfills my need. And so I'm going to label this y equals sine x. And this is my parent function. So as a rule, we can identify these properties right from the start. So domain, we were given that is negative 2 pi to positive 2 pi. I'm going to default to interval notation, just as a heads up, not set notation. If you like to use set notation, you're more than welcome to. My range, well, that's my y values, and as mentioned before, I have a minimum of -1 and a maximum of 1. The period, I always like to start at the bottom of a curve for sine because it starts at 0. So I look to see, okay, well, when do I end up back in a position where I'm not only hitting 0 again, but I'm going to be going upward again. So if I imagine my curve continuing here, it would look something like that. And so you'll see that it starts to repeat itself. So my period goes from 0 to 2 pi, because that's when I kind of end up in the same place. And that fits with us going around the circle, because once we've gone around 2 pi, well, we're doing the same thing again, and again, and again. We end up in the same angles, no matter where we're going, how many times we've gone around. So the period, I would say in this case, is 2 pi. The amplitude, again, that's the height from the midline, or my 0 in this case, because that's halfway between the maximum and minimum, to my maximum is 1. Now the amplitude is always positive, so that's what I would write. I always go to the maximum for that reason. And then my zeros, I could write a general equation for it, because 0, pi, 2 pi. So 2 pi times k, where k is an element of the integers. And again, we've seen this notation before already. So some people use I as the integer symbol. I use Z. They're both acceptable, as long as you're saying that 2 pi k is your zeros, and k can be any whole number, positive or negative. Let me see that. And you know what, it's actually just pi, not 2 pi. So we got pi, 2 pi, 3 pi, 4 pi, 5 pi in both directions. Doing cosine is much the same, but remembering that it's our x coordinate. And so instead of starting at 0, my x-coordinate starts at 1. It goes to 0, and then reaches its minimum at -1. So again, we have the same maximum and minimum. They're just happening in different places. So I'm going to draw them in. 1, -1, again, I'm going to only break this down very minutely. So to negative 2 pi and positive 2 pi. And that's really all the labeling I have to do of my graph. If I wanted to do more, I could add in these ones. I could keep subdividing forever, but I am going to be efficient here because you've already done this. So again, I start at 0 radians. So I'm starting at this point right here on my x-axis, which means that my value is 1. So that's where we start. Then we travel along to pi over 2, and that's where we hit our 0. We hit our minimum at pi. So whereas in our sine graph, we're hitting zeros at 0 and pi, in our cosine graph, those are our maximum and minimum. So we can already predict maybe what it's going to look like. And again, with a maximum and a minimum being established, because we can see that in the circle, we can't go past 1 in either direction, because our circle is a radius of 1. Makes life easier for predicting my graph. Okay, so from here, I'm going to do the exact same thing. If you plotted those individual points that were between these, you would have gotten a lovely curve. Cosine's sometimes easier to draw than sine. There we go. So again, you'll see that same curved shape, just shifted over, starting at 1. That is for y equals cos x, and that's going to be our parent function. So if you remember that cosine always starts at 1, goes downward, and its period is still 2 pi, because we still go all the way around the circle before we start repeating ourselves, you're going to be good to go. So our domain, we were told, is negative 2 pi to 2 pi. The range, as established by the fact that we're working with the unit circle, is a maximum of 1, minimum of negative 1. Amplitude is 1 because we're going between those two values. My midline's at 0, so going up would be to positive 1. And my zeros in this case would be pi over 2 times k, where k is an element of the integers, because we are seeing it at pi over 2, 3 pi over 2, 5 pi over 2, negative pi over 2, negative 3 pi over 2. So it still is exactly pi between them. We're still doing exactly a semicircle between my zeros. It's just that now they're not on as nice of numbers. They're not on exactly pi. They're on half pi's. Now, tan is the one we haven't seen before, so I'll make a separate video about it, and we'll leave it for now. So moving the parent function around, that sine x or cos x around the Cartesian plane, which is just our coordinate system of x and y, okay, is called a transformation. So we're going to have a whole unit on that. That's unit number 2. And we're going to work with it for the rest of the year almost. So that's a really good word to remember. And in general, for all of them, for any graph, any function at all, we talk about the transformation looking like this. So we've got A, B. Here we see H and K. We also can call that C and D. And that's usually where I default to. Okay, H and K ties in the idea of like quadratics that you would have seen in grade 11. So the amplitude, as we saw, gets multiplied out in front. We think of it as the absolute value, so always positive. Looking at these examples, my amplitude here is 2/3. It's totally allowed to be a fraction. That is fine. And the amplitude for my second one here, even though there is a negative there, I would still say the amplitude is 4. So what does this do to my graph? Well, it's that vertical stretch or compression. So typically, I'm going to draw y equals 2 sine x first. Typically, my range is going to be, or my maximum is 1 and my minimum is -1 in this case. Now it's going to be, instead of 1, it will be 2 and -2. So we're seeing that sort of vertical stretch. It does not change my zero values at all. So it doesn't give us a specific range that we need to draw in, so I'm going to probably work from -pi forward. So pi, probably only go to 2 pi still. I could keep going, but I don't see why it would be necessary. So my zeros stay the same, so sine starts at 0 and repeats every pi. Okay. My maximum is usually, and then my curve goes upward as I follow the circle going upward in my angle. So that's where I'm going to hit my maximum now at 2. My minimum will be at -2. And same thing over here, minimum at -2. Once I've got these key points plotted out, again, it's just a matter of matching my shape to what we know a sine curve is supposed to look like. And it's going to be a little bit more narrow, a little bit more V-shaped than we would have otherwise liked it to be, because we are stretching it out. Now, because my domain is not restricted, I am going to put arrows on the ends of these now, because it could keep going. I could have chosen a different range of or domain to work within. So that's how I would sketch that one. For half cos, this is a compression as opposed to a stretch. So when I draw this, I might choose to just have 1/2 and -1/2 as my maximum and minimum y values. And that's totally within your right to do. And for me, I just find it makes it easier than trying to squish things into a very small space. I'm going to work with the same range, -pi to 2 pi. Remembering that cosine starts at 1, goes to 0, -1, and again, my period is not affected by the change in amplitude. So I still know that I should end up in the exact same spot when I end up back at 2 pi. And from here, I can fill in my curve. So we have a lot of examples like this. Like that one. There we go. And again, I would throw my arrows on the ends to acknowledge that I don't have a restricted domain or range, technically. The period is related to B in the sense that it is actually 2 pi divided by B. Okay? period for tan is a little bit different, and again, we'll come back to that one. But in general, the interval will be the new period divided by 4. Okay, so again, this is kind of like how much I would when I would expect to have to repeat my sine function. So in example 3, we can quickly pump through these using the formulas from above, so maybe I'll scroll down so far. If b is 6, then my period is going to be equal to 2 pi over 6, which is the same as pi over 3. B, in this example for part B, is 2/3. So period is pi divided by 2/3. Again, when I'm dividing by fractions, it's like multiplying by the reciprocal. So really this is going to be 3 pi over 2. Finally, for C, got sine equals x over 7. In that case, that means that b is 1/7. Okay, so if we just end up with a denominator, if you tried to like take out the x, you'd be left with a 1 in the numerator, saving its place. So that would be 2 pi divided by 1/7, or 14 pi. So something that you might have noticed as you were playing on Desmos is that a larger value for b means a smaller period versus the 2 pi that we'd be dealing with usually for cosine. Same thing, we see that for sine. The b value that's between 0 and 1 resulted in a much bigger period, or b value, or period is correct, compared to 2 pi. So when we go to sketch these, we're going to keep our maximum and minimum at 1 and -1 because we're not influencing the amplitude at all. But instead, we're going to change what our domain looks like. So I'm always going to be inclined to actually figure out what my period is first before I start filling this in. So period in this case is going to be 2 pi divided by 2, so just pi. So whereas before I would have divided this in and gone up to 2 pi, I'm going to kind of zoom in on my graph a little bit and say that this is going to be pi over 2. And I'm going to expect my graph to all of a sudden repeat only at pi. Okay. So again, I'm only going to go to negative pi over 2 over on the left-hand side. So when I graph this, everything else stays the same. It's just that horizontal piece that just changed. So what I'm going to see is my sine graph still starts at 0, but it's going to hit 0 again at pi over 2 and pi. And that's where I'm going to repeat. So I should expect my graph to look something along the lines of these. Now you can plug in values into your calculator. There's nothing that says that you can't be using your calculator to determine these, but you do want to become more and more comfortable with the sort of idea of landmarking points from a parent function and figuring out where they belong when we've transformed a graph. And I'm going to work hard to make sure that my curves look like curves and not like V's. We're not doing absolute value graphs here. And that would be my graph, roughly. This is a little high, it should be a little lower. Okay. Conversely, for y equals cosine half x. My period would be 2 pi divided by half, which would be 4 pi. So in this case, instead of being subdivided into smaller pieces, I would go so far as to say that even if I did divide it like I did in my earlier examples, I'm just going to have to go farther before I'm able to actually complete one full set of my curve. So let's make this a little bit more obvious. Okay, so cosine again starts at +1. Because my period is 4 pi, I won't reach +1 again until 4 pi. In the middle of that, so at 2 pi, that should be where my minimum is. And my zeros should be halfway between that. Which gives me a sense of where my zeros are, where everything should be. And again, I can start doing my landmarks. You will see in this curve that all of a sudden it becomes much wider. Like so. And again, we would want to include those arrows to acknowledge that our range does continue, or our domain does continue. So I hope that that is making sense in terms of like how to landmark these graphs as well as how these different pieces work. Phase shift is specifically horizontal distance, or C, so we're seeing those as subtracting. So that's the one key thing to notice about anything that affects x within the brackets, like within the function, kind of seems to have an opposite effect. So up here we saw that half influenced my period and that it became twice as big. Here, when I do a phase shift, because it's subtracting in my general formula, when I actually go to identify my C value from any equation, it changes the sign of the number that's in there, which means it kind of seems like it's doing the opposite of what it looks like. So determine the phase shift of the function y equals sine x plus pi over 4. Well, that means that C is actually going to be negative pi over 4, because two negatives would make that positive there in the equation. Conversely, when we're looking at the second example, C would be positive pi over 6, because in the general equation we are subtracting. So what does that mean for when we sketch? Excellent question. It basically just changes where we start drawing our curve. So for y equals sine x minus pi over 2, I would identify my my phase shift, as being positive pi over 2. So instead of starting at 0, I'm going to be starting at pi over 2 instead. So that's how I'm going to break up my graph, so I know where that's starting. Without any other numbers in this equation, I am still dealing with a period of 2 pi now, because I've gone back to my b value being just 1, because it's not really there. My amplitude, there's nothing out in front of my function, so it's still going to be to the positive and negative 1 as my maximum and minimum. So I'm going to start at pi over 2, but I'm going to keep all my points otherwise the same. So whereas my next 0 would have usually been pi, so I'm going to shift it over 1. Pi, 2 pi, 3, 4. Okay, so all of my zeros are going to be shifted over. Okay. We're also going to see that in terms of my maximum. If this is my starting point right here, my sine graph always went up first to its maximum and then down to its minimum, up to the maximum, too high, down to the minimum, and over here as well. Oops. Missed one. Minimum and maximum. That's why we want to be careful on making sure we don't miss anything, because it can totally mess up our graph. From here, drawing our curves as usual. Let's go extend it that way. Okay, so again, that red point there is my starting point. For cos x plus pi, what we would do is, again, amplitude stays the same. The period is going to stay the same, so I'm going to keep working with the whole idea of pi and 2 pi. And negative pi. But instead, my C value here is negative pi, so that's where I'm going to start. Cosine starts at its maximum, so my first point is going to be here. Because my usual period goes from 0 to 2 pi, if I've moved it a whole pi over, I should stop. I should start repeating myself again at just positive pi. That's where my next maximum is. From there, I can fill in halfway as a minimum, and my zeros are halfway between them. And I keep filling this in further. You can just do your best to try and make sure your points are consistently in line. So if this was my starting point, maybe I'll make it a little star here. Again, I'm just going to make my curve. And extend it out. So that's phase shift. Now our midline, or middle, you might see, or vertical translation is represented by D. It's added at the end. So again, going back to straightforward signs meaning what they mean. For the midline, or D value here, in this equation, we're looking at the constant kind of tacked on at the end, so it would be -1. Here, it would be +3. So in this case, it is going to change my vertical range where what I'm working within. I'm still going to be above it by 1 and below my midline by 1. That part doesn't change, but in terms of where I'm actually showing that here, that will change. So my first one for y equals sine x minus 2, that means d is -2. So my midline is happening here instead. From there, my max, okay, and my amplitude is 1, so my max is at -1, and my minimum is at -3. So this is where it gets a little tricky. We want to be really conscious not only of where that midline goes, but also how that impacts how I should be scaling my graph and how far down or how high up I should be going. So -2 is here. Horizontally, it has no impact on it, so I'm going to still use the same scale. I'm going to not draw as much though, just in terms of time. So I use the same starting point. So sine usually starts at 0 at my midline, so it should be starting at -2 because that's my new midline. From here, I shouldn't repeat myself again until 2 pi. Halfway between it is my other 0. So every pi is still going to be quote-unquote 0, except now they're not zeros at all. It's just where they're going to land on the midline. So that's why I like to just kind of sketch in where my midline would be. It provides that point of reference of the quote 0. Once I've got those, then I can go for my maximum and minimum. Sine always goes up first. But I'm not going all the way up to 1. I'm only going up to -1. Only 1 above my midline, because that's the amplitude. And for my minimum, I'm only going to go 1 below my midline. So there. So in this case, it looks like my graph is condensed. That's only because I'm using the same size of axes. The main thing is that I'm staying entirely below my x-axis, that I don't go above -1 and I don't go below -3. That midline is -2, halfway between your maximum and your minimum. Your other equation is y equals cos x plus 1. So we're going to see that the d value is 1. My amplitude is still 1 because there's no number out in front here. So that means that maximum is at 2 and minimum is at now positive. It is at 0. Sorry. So again, when I draw this, I'm going to scale my y-axis appropriately. It doesn't really matter what my scale looks like in the bottom half of it, because I'm not going to be going down there at all. Horizontally, I'm going to use the same scale I've been using for the most part. Two pi. I'm going up by pi over 2s. So again, cosine starts at a maximum, which we said was 2. My midline is at 1. Oh, that's a bit messy over here. Okay. And I shouldn't repeat myself again until 2 pi. So I'm not going to get back up to that maximum until 2 pi. From there, I can fill in My minimum should be halfway between my two maximums, zeros between them. That gives me my predictability to keep filling in the left-hand side or beyond to the right. And again, I'm going to draw my curve. So you're going to feel like you are drawing curve after curve, and you will be. And that's okay that you feel that way, because the only way you are going to feel truly confident in your skills for drawing sinusoidal functions, and also for being able to draw these different transformations and predict them with ease, is by doing this a lot. So you're feeling sick of it? Great. You should be, and you will continue to feel that way. So this is our summary of the last 2 lessons condensed into one, and also a summary of what you saw with respect to our explorations. I hope that makes sense. If you have questions, because this was a little bit rapid fire, you're more than welcome to let me know, and we can kind of talk about it a little bit more. I can go more in depth. I'm going to release another video that looks specifically at tan, because as we see right here again, tan is a little bit of a different beast in comparison to sine and cosine. But I hope that helps, and we'll continue with the next lesson tomorrow.